In this video, we're going to talk about some more subspace examples. So let's dive right into it. So if I'm given a vector space V, test if H is a subspace of V. So in part A of this example, V, my vector space is P2. So remember, this is the, actually let's write it up here. This is the set of polynomials of degree at most 2. Degree at most 2. That's what this notation means. And H is the set of P of t that are in P2. So this is polynomials in P2, polynomials that have degree at most 2. Remember, the colon means such that, such that P of t equals AT squared plus BT, where A and B are reals. Okay, so the polynomials in my set have this form. They look like this. Okay, so let's talk about how to solve this. So I need to check to see if this is a subspace or not. So because I'm testing to see if it's a subspace or not, I'm not sure whether this will be a subspace or whether it won't be. So I need to form some intuition behind that. And if I'm not sure what the intuition is, I need to just start checking the 3 properties. So for this problem, let's say I wasn't sure. Let's say I wasn't sure whether this was a subspace or not. What we could do is we could start checking the properties one by one. So let's take a look at what that would look like. So the first property is 0 in H? And notice that this time when I've written this, I've deliberately not written the word the 0 vector, because my set doesn't contain vectors. It contains polynomials. So I'm just asking, is 0, sort of like the 0 element, in H? Is it in my set? Okay, well, what's 0 when we talk about polynomials? Like, what is the 0 polynomial? So the 0 polynomial is the polynomial P of t that equals 0 for all t. So no matter what t is, the output is always 0. So is this, actually, let's draw a picture of this. Let's see if we understand visually what this looks like. So if I draw my xy axes, the graph of P of t equals 0 is just the y value is always 0. So no matter what t is, think of this as the t-axis, this is the y-axis. The graph is just this red thing. That's the graph of P of t. Okay, so that's what the 0 polynomial looks like. So is this in H? Is it in our set? Does it look like this? Does it look like something times t squared plus something times t, where these things in these parentheses are reals? And the answer is yeah, because I could just put zeros in for both of them, and that gives me 0. And notice that this also kind of looks like a linear combination, and that's kind of by design. Vector spaces, in some sense, are supposed to be like Rn. Okay, so the 0 polynomial does have this form, so it is in H. Okay, so P of t equals 0. Our 0 polynomial is in H, so that means this first property is true. So let's check the next one. So let's check now to see if we have closure under addition. Oops, sorry, I think I'm going to spell closure. Closure under addition. And I'll put a question mark after it. So let's check this. Is this set closed under addition? So to check that, I need to take 2 elements in H and then add them together and see if that's still in H. So let's call these elements P of t and Q of t, because they're both polynomials. So what does something in H look like? Well, it looks like, some coefficient times t squared plus some coefficient times t, where the a and the b are going to be reals, and Q of t I'm going to have be some other polynomial, so it may have different coefficients. I'll write c t squared plus dt, and a, b, c, and d are real numbers. Okay, so both of these things are in H. And now I need to add them together and see if when I add them together, it's still going to be in H. So if I add these and get P of t plus Q of t, so we've done stuff like this in the last video. But when I do that, I will get a plus c times t squared plus b plus d times t. And this has this form. It's something times t squared plus something times t. So this is in H, which means closure under addition is satisfied as well. So there's one property left to check, which is closure under scalar multiplication. So closure under scalar multiplication. So let's check this. So to check this, I need to take an element in my set. So I'll call it P of t, because the elements are polynomials. So an element in my set looks like at squared plus bt, where the a and the b are reals. Okay, and then I need to take some scalar, some arbitrary scalar. So I'm going to let c be that scalar. It's going to be an element of R. And then I need to multiply these together. So when I look at c times my polynomial, I need to see, is this still going to be in my set? Is it still going to be in H? So if I multiply c times at squared plus bt, we can distribute the c. And if we do that, we get ca times t squared plus cb times t. And overall, this still has the form that things in H are supposed to have. It's something times t squared plus something times t. So this is in H. It's in our set. So we do have closure under scalar multiplication. So because all three of these properties are satisfied, that means H is a subspace of our vector space, which was P2. H is a subspace of P2, since all three properties hold. All three properties hold. So testing to see if something is a subspace is similar to testing if something is a vector space, in that if I want to show something is a subspace, I need to show all three properties hold, like they did here. But if I want to show something is not a subspace, I need to just show that one of the properties does not hold. Okay, so let's do another example. Okay, so let's say I had, so this is part B, let's say I had my vector space being P2 still, so polynomials of degree at most 2. And this time, H is the set of polynomials in P2, whose formula looks like P of t equals at squared plus 2, where a is a real number. Okay, so having done the last example, and having a feel for, what is a zero polynomial, what does addition look like with polynomials, what does scalar multiplication look like with polynomials, I want you guys to pause the video for about a minute and think about this question. Think about whether you guys think those three properties will hold, or if there's one property that you guys see is not going to hold, or maybe even more than one. So 4, 3, 2, 1, pause the video. Pause the video for about a minute and think about this. Okay, so hopefully you guys have done that. Hopefully you guys paused the video and thought about it. Okay, I'm going to start to talk about it now. Okay, so let's consider the zero polynomial. Let's consider the polynomial P of t equals 0 for all t. So that's the zero polynomial. And let's ask ourselves, is this in H? Does this polynomial have this form? Does it look like at squared plus 2? And the answer to that is no, because there's no way I'm going to produce this 2. The constant term doesn't match up. So this polynomial is not in H. It's not in H, since the constant term in the zero polynomial is 0. It's not 2. The constant term is not 2 like we need it to be. So already the first property of a subspace is 0 in my set is not satisfied. And as a result, I'm done right there. Therefore, H is not a subspace of P2. Okay, so H is not a subspace of P2. Let's box that. And let me go ahead and also box in our answer from the other part, from part A. So again, just to reiterate, if I want to show something is a subspace, I need to check all three properties and make sure they all hold. If I want to show something is not a subspace, I just have to find one property and show that one property doesn't hold. In part B, we kind of got lucky, and the first property we checked ended up showing that it wasn't a subspace. Sometimes we might have to try it a little bit, and maybe the first one works, but then we tried the second one, and the second one doesn't work. And that's how we formulate our argument. Okay, so let's do one last quick example. So example 7, is R2 a subspace of R3? So is R2 a subspace of R3? Okay, so at first glance, it seems like this is a pretty reasonable statement. Like R2 is, in some sense, some sort of two-dimensional thing. It's a two-dimensional plane. Is that going to be in R3? Is that going to be a subspace of R3? Okay, so the elements of R2 look like this. They're vectors with two entries. I'm just going to call them X and Y. But what do the elements in R3 look like? The elements in R3 have three entries, X, a Y, and a Z. Okay, so because of that, the things that are in R2, they are not in. We cannot say that these are in, that they do not live in in R3. So the elements in R2 are in a completely different universe than R3. They don't live in R3. They're not elements in R3. So because of that, the answer to this is no, kind of right away. It's no, since the elements in R2 are not even in R3 in the first place. Are not in R3 in the first place. And this is, a very subtle point. So I'd encourage you guys to pause the video and, even rewatch it and think about it. But for something to be a subspace, for some set H to be a subset of some vector space V, I need the things that are in H to be in V in the first place. So like, for example, if I go back to this earlier example, the things that are in H, part of what it said is they're polynomials that are in P2 with some additional property, but they're in P2 for sure. And our vector space was P2. So that's important. The things that are in H need to be inside of the universe of V. But in example 7, the things that are in R2 are not in the universe of R3. They're not elements of R3. Okay, so there's one final remark I want to make about this example, and that is, there is a way to sort of restate this, what this example is saying, so that it is true, but I need to change what H looks like. I need to change H so that it consists of vectors with three entries. And the way I would do that is I would write it as X, a Y, and I would make the third entry 0. These are different from things in R2, because this has three entries. So such that X and Y are elements of the reals. And if I look at this set, it turns out is a subspace of R3. Vectors in H live in R3, like they each have three entries, so they're elements in R3. And moreover, this set, it turns out, will satisfy those three key properties. It has 0 in it, it's going to be closed under addition, vector addition, and it's closed under scalar multiplication.